Hello everyone, welcome back to my channel. I hope you found the previous video I uploaded useful. Today also we'll be continuing on from the point where we left off. In the previous video we'll be talking about concept of equilibrium and we'll be talking about an example, and then we'll be moving on to discussing what chemical and physical equilibrium is. So in the previous lessons we were focusing mainly on the concept, and in the upcoming lessons we'll be focusing mainly on problem solving, and we'll be focusing on equilibrium constants. So I do hope that you find even these lessons quite useful, and please do let me know in comments below what areas you want me to cover in the future. Let's get on with the lesson now. So let's start with the lesson. Equilibrium part 2. What we learned last week was mainly related to concept of equilibrium, so we'll be kind of looking at that a little bit today as well, and then we'll be moving on to chemical equilibrium and physical equilibrium. Just to recap on what we did last week, these are the main 3 points I want you to remember. At equilibrium, product and reactant concentrations remain the same. At the same time, make sure that you remember the fact that at equilibrium, rates of the forward and the backward reactions also remain the same. The starting point, so when it comes to starting point of equilibrium reactions, normally it doesn't matter from which end we start, right? We can start with the reactants or we can start with the products. Doesn't matter from which end we start, it will always attain a equilibrium in a closed system. So which brings us to the third point that we shouldn't forget, which is equilibrium will not be attained if it is not a closed system. We can only obtain equilibrium when we do a reversible reaction in a closed system. If not, reactants or products can escape out, and so therefore we will not be able to obtain an equilibrium. So if you want to kind of learn about that part in detail, you can watch my previous video that I will be linking down below, and you will have a better idea about what I was talking about here. Now, for this example, I have actually taken N2O4 going into NO2. When you're starting with N2O4, now these two graphs, guys, I just want you to know that the one on the top is concentration versus time graph. One on the bottom in each of these diagrams is rate versus time graph. So when you're starting off, the blue color represents N2O4 and the brown color represents NO2. So when you're starting off, the concentration of N2O4 is high because we are only starting with N2O4. So N2O4 will break down and produce NO2. So as and when you start producing NO2, the concentration of NO2 will keep going up. If you can see my cursor, you see as N2O4 concentration keeps going down, NO2 concentration keeps going up. So you can see the concentration of NO2 keeps going up faster than NO2 concentration keeps going down. That is because from one NO2 molecule, there are two NO2s produced. So the concentration of N2O actually increases twice as fast compared to the speed at which N2O4 get consumed, right? So when N2O4 concentration keeps going down, NO2 concentration keeps coming up. We are clear about that. But at one point, these concentrations kind of become a constant. It doesn't change. It doesn't keep increasing or it doesn't keep decreasing. Why is that? To look at why that happens, we can take a look at the rate versus time graph. So you know, concentration and rate are having a good relationship. So basically, when concentration is high, the rate will be high, and when concentration gets decreased, the rate will also get decreased. So you know, when you're starting off the reaction, concentration of N2O4 is quite high. So the rate of the reaction is starting from a really high point. As the concentration of N2O4 decreases, the rate of the reaction or the forward reaction also decreases. Rate at which N2O4 converts into NO2 decreases as the N2O4 concentration decreases. As it happens, more and more NO2 is produced. So N2O4 concentration goes up. So NO2 concentration goes up. So initially NO2 concentration is 0. So the rate at which the backward reaction happens, which is NO2 getting converted into N2O4, is significantly low. So initially the rate of the backward reaction is 0 because you don't have any NO2 produced to begin with. But when N2O4 converts into NO2, little by little the NO2 concentration comes up. That means the rate of the backward reaction also increases. Why? Because when NO2 concentration goes up, the rate at which NO2 converts into N2O4 also go up because of the concentration increase in NO2. So the backward reaction rate keeps increasing, whereas the forward reaction rate keeps decreasing. So at one point, backward reaction rate and the forward reaction rate becomes equal. They obtain the same value. So at this particular point, when forward reaction happens, the same speed the backward reaction happens. So that means N2O4 gets consumed to produce NO2, and at the same time, the same amount of NO2 that was produced will react and form N2O4 back. So the concentrations of each of these reactants and products will remain a constant. That's what you can see in this picture. So at this particular point, the rates of the forward reaction and the backward reaction are the same. So therefore, the concentrations of N2O4 and NO2 becomes a constant. They do not become 0, they become a constant. Because as much as it is converting into products are converting back into reactants at the same speed. So in an equilibrium mixture, it is never a reactant or a product is never going to have a 0 concentration when equilibrium is achieved. So I hope you have a better understanding about obtaining the equilibrium now just by looking at these diagrams. So I want you to have an idea about having an equilibrium reaction starting from products or reactants. Now, graph A shows us that we can start the reaction from the products end as well. So just imagine the same type of vial which is vacuated, and you introduce to that vial only NO2 gas, right? That's what has happened here. So the concentration of NO2 is significantly high, and there's no concentration of N2O4. So with time, NO2 concentration will keep going down. Why? Because it is getting consumed and it is conducting the backward reaction, producing N2O4. So when N2O4 is produced more and more, the concentration of N2O4 increases, right? At one point, these concentrations will become a constant because rates at which NO2 converts into N2O4 and N2O4 converts back into NO2 becomes equal. So at one point, when forward and backward reaction rates become equal, the concentrations also will become a constant and will obtain an equilibrium, right? So you can start from products and obtain an equilibrium if the reaction is a reversible reaction. This is another example. You can start again from a really high concentration of N2O4 and start producing NO2 and obtain equilibrium. So it doesn't matter from which end you start, you can obtain an equilibrium no matter whether you only have the reactants or whether you only start with the products. That concludes the concept of equilibrium part. Now we'll be looking at different types of equilibrium that we have, right? Equilibrium in physical processes. It can be broken down into these 4 categories. So most of the physical processes in equilibrium relates to transition from one phase to the other. For example, solid liquid equilibrium. So solid phase turns into a liquid phase. Also, in this particular case, you have a equilibrium, liquid vapor equilibrium, and solid vapor equilibrium, and solid solid equilibrium. So I'll take each one at a time, and I'll explain it to you. So, as you may know, if water is the most familiar substance for us when we are talking about equilibrium, and when you're talking about anything related to chemistry, you encounter water quite a lot. So it's a good example to take even here. At 0 degrees Celsius, you say water's freezing point is 0 degrees Celsius, or you say water's melting point is 0 degrees Celsius. What exactly happens here is, at this particular temperature, at 1 atm pressure, there is an equilibrium that prevails between liquid water and solid water. Right? We call water and ice. So when at a particular temperature, at 1 atm pressure, when a solid and a liquid are both present in equilibrium, that particular temperature is referred to as the melting point or the freezing point. So definition is given here. For any pure substance at atmospheric pressure, the temperature at which a solid and a liquid phase are at equilibrium are called a normal melting point or normal freezing point. So at this point, the liquid water converts into solid water at the same speed as the solid water turns into liquid water. Right? So this particular point is called a liquid solid equilibrium, or you can call it the boiling point or the freezing point of water. And then you have liquid vapor equilibrium. So it's the same scenario. If you just change the phases in this particular definition, you will have the meaning of liquid vapor equilibrium. So for any pure substance at atmospheric pressure, the temperature at which liquid and vapor phases of water are at equilibrium is called a normal boiling point of that particular substance, right? So boiling point means where the liquid phase and the gaseous phase of that particular substance is at equilibrium at 1 atm pressure. Solid vapor equilibrium is obtained if you have a solid and its vapor in a closed system, converting into, let's say, solid converting into its gas and gas converting into its solid at the same rate in a closed system at 1 atm pressure. We call it a solid vapor equilibrium. So we can see this happening in iodine. If you take a small piece of iodine and place it in a closed container, after some time you will be able to see a small the container or the gas inside the container turning, not the gas inside the container, space inside the container turning to a light purple color. After a while, the purple color will increase, and at one point the color will stay a constant. So at this point we can say there's a solid vapor equilibrium achieved where iodine gas converts into iodine solid at the same speed as iodine solid converts into iodine gas. Alright, very simple guys, there's not a lot of complications there. And another equilibrium that you see is this transition equilibrium, where now let's say you have a solid piece of sulfur. So without changing its solid phase, right, you see it doesn't change into liquid or vapor, it is changing its crystalline structure. So when it is changing its crystalline structure, for example, solid has sulfur is converting into rhombic sulfur, from rhombic sulfur to monoclinic sulfur. So at a temperature, at a given pressure, which is 1 atm, let's say for 1 atm, the temperature at which sulfur, rhombic sulfur and monoclinic sulfur phases are at equilibrium. That means they keep changing from rhombic to monoclinic, monoclinic to rhombic at the same speed. This particular point is known to be the transition point of sulfur. Chemical equilibrium. Now, for the rest of this lesson, starting from the next lesson, we'll only be focusing mostly on chemical equilibrium. All of the calculations, all of the laws of chemical equilibrium and equilibrium constants, mostly we'll be discussing for chemical equilibriums. So when it comes to chemical equilibrium, there are two main types: homogeneous equilibrium and heterogeneous equilibrium. Guys, science is quite simple, especially when it comes to terminology. Homo, if you ever see in any place the word homo stands for same, hetero stands for different. So homogeneous means same phase equilibrium, heterogeneous means different phases equilibrium. So that means, if I'm breaking it down, that if all of the reactants and the products that we are looking at in a particular reversible reaction are present in the same phase, we call it a homogeneous equilibrium. For example, the first reaction that I've given is a gaseous phase equilibrium where all of the reactants and the products are present in gaseous form. So this is gaseous phase or gas phase equilibrium. And then you have another example where all of the reactants and the products are present in liquid form. So that means this is a liquid phase equilibrium. So these are all homogeneous equilibrium because you have the same phase in both reactants and products. Now guys, if you take a look at this, sometimes some of you all might be confused. Sometimes people think whenever there's water present in an equation, that means everything in products or reactants, everything has to be written as aqueous because water is present. One thing you have to understand is they are starting with two organic compounds and producing water as a product, so in smaller quantities. So here, if you kind of go back and change these physical states to aqueous, you are making a mistake. Just because there's a little bit of water doesn't mean it kind of overpowers the entire system to make water a solvent and have the physical states written as aqueous. It is a mistake some people make. Just want to emphasize on that when we're moving forward. So since it's made in very small quantities, not necessarily very small, in small quantities, it is going to be present as liquid water, and all the rest is also going to be present as its liquid form. Moving on to the main topic, the second type of the chemical equilibriums that we find are heterogeneous equilibriums. Heterogeneous stands for different phases equilibrium. For instance, the first example you have here, calcium carbonate is a solid, and calcium oxide that is formed is also a solid, but you have a little bit of gas, carbon dioxide formed. So reactants and products are not in the same phase. Some of it are present in the solid phase, some of it are present in gaseous phase. Even in the next equation, iron and water, iron is present in solid phase, water is present in gaseous phase, it's actually steam. And then you have ferrous ferric oxide, which is present in solid phase, and water, that is hydrogen, that is present in gaseous phase. So products and reactants are not present in the same phase, so therefore we call it a heterogeneous equilibrium. So we will learn how to calculate the equilibrium constants and the laws of equilibrium in the next lesson. So stay tuned, guys. And all of this content, most of it is taken from the resource book that is provided by the government. You can actually go and check it out. I'll link in the description where you can find the textbook or the resource book for this particular lesson in my bio. So please go check it out. Thanks for tuning in. If you have any suggestions for future videos, please do let me know.